Hello everyone and welcome back. So this time we're talking about normal stresses in beams. Now last time we ended with this equation. I said it's not really all that helpful because what in the world is the radius of curvature? Like, where is that? And also, this distance y right here is from the neutral axis, this neutral surface, this point where our stresses go to zero. And we have to wonder, well, where is that? Where is that point? So today we're going to answer both of those questions. So for our neutral surface, to figure it out, we're going to be looking at the cross section right here. And we're going to look at a little area dA. That's a distance y from our neutral surface. Now, we don't know where this is yet, but we're just saying, it's the distance y. It's all variables right now. Now, all of our normal stresses which are acting on that point will cause a resultant force dF, an infinitely small resultant force. But to maintain equilibrium, all of those forces must sum to zero. Now, remember from our previous little view, if we're looking from the other direction, we're going to have stresses going in one direction, above the neutral surface, and stresses going in the opposite direction, below the neutral surface. Something along those lines. And so those are going to have to cancel out. Okay, so it makes sense. That gives us one equation. Not quite enough, though, to solve for what we need. So let's keep going. Now, if we plug in everything we saw beforehand, we can say, okay, well, the sum of the forces is going to be equal to my distance from the neutral surface, dA, multiplied by this factor right here, which is the radius of curvature and modulus elasticity. Now that y dA, that's going to be important, so just let's hold that there for now, and we'll come back to it. It is a very important detail for us. Now that can only occur if the neutral surface passes through the centroid of the cross-section. Why is that? Well, that's because the centroid location is always y dA over integral of dA. Okay? Y dA over integral of dA. So we can only have that happen if everything goes through the neutral surface. It's only going to work then. That's where that y dA is coming from. Okay, so now we know that our neutral surface, so our neutral axis has to go through our centroid. So we know how to calculate centroids for any arbitrary shapes. That's a good thing to know. But we got a little bit more to figure out here, because we have that E over rho, which is not very helpful. So how are we going to get rid of that? Well, we're looking at the same thing. We have that same force dF. And that force is going to cause a moment. It's a force at a distance. Remember, distance, force, that's going to create a moment. And so we have an equation that looks something like this. Our moment is going to be equal to our little stress equation times dA times the distance y. But just like with forces, all of these bending moments have to sum to zero to maintain equilibrium. We can't have any element breaking equilibrium. So we sum them all, and they should equal zero. If they don't, we're lost. Now this M right there, that's the internal moment, just to be clear. Now if we then substitute in our equation for normal stress, we can get the following. So our moment is going to be equal to, this is solving for that internal bending moment, equal to the modulus elasticity over radius of curvature times integral of y squared dA. And this last term is the moment of inertia, which is something that you can also calculate using, if you look in your textbook, you can find out what the moment of inertia is for rectangles and circles and triangles and everything else. So now let's go and figure out our equation for internal bending moment, and we can write it as follows. So the moment is equal to our moment of inertia times modulus elasticity over radius of curvature. And I think that you're going to begin to see how I'm going to simplify that earlier equation, because we don't want the radius of curvature. That's the one that we want to get rid of. And we can, thanks to our moment. So using our internal bending moment, we can then redefine our normal stress as this. Where my normal stress is simply my distance from my neutral axis times the internal bending moment over the moment of inertia. This is called the flexure formula. And this one is actually useful. You're like, why do you give us all these useless equations if there's going to finally be one that's useful? It's good to see where things come from sometimes. I don't always do a whole bunch of derivations, but I like for you to see the buildup. And it's a valuable skill to have, to realize that an equation that you have isn't all that helpful if you don't know how to calculate one of the variables. So sometimes you have to redefine things. Okay, finally, some sign conventions here. Bending stress is caused by a positive moment. Positive moment right there. Remember, positive moments bend it into a smiley face. They're going to be in compression on the top and tension on the bottom. The way you can tell that is that this is pulling it on the bottom and it is pushing it in on the top. And it's always resisting that. For negative bending stress, it's going to have tension on the top and compression on the bottom. And there are some cases when you have like something that's, not actually a nice steady cross section, where you won't have any compression or any tension at all because of the eccentricity. We'll get to that next time though. Okay, I think that's everything. I think we're going to examples. Yes, we are. So I'll stop here and I will see you all next time as we start doing some examples. So thank you very much for listening. I'll see you later. Bye-bye.